Okay, so now we're dealing with a variable force. And so for the variable force, it's just the integral from a to b of our variable force. Just like we did before, that was our constant force. So let's take a look at one. We want to see a particle is located a distance x feet from the origin. A force of x squared plus 2x pounds acts on it. How much work is done in moving it from 1 to 3? So all we have to do is go, okay, we're moving it from 1 to 3 of x squared plus 2x dx, and then plug it in our calculator and it gives us an answer, which is 16.7. So 16.7 foot-pounds. So the reason I know that is x is in feet and this is in pounds, so it's foot-pounds. Now, just doing this doesn't really do anything for us. We need to make sure we understand what's going on. So I've already graphed it, and this is our force that's being applied. So if you plug in 1, it tells you the force that needs to be that's being applied here. And then if you plug in 2, it tells you the force that's being applied there. So again, we're just thinking about that rectangle. So the height of that rectangle is x squared plus 2x, and the thickness is dx. So that is the work that's being applied because it's force times distance. Now what we're doing though is then adding up all of those rectangles in this form. So this rectangle represents the work for that one rectangle, and we've got to take and think about it as every single rectangle going through there. And we end up with this integral. So this integral is adding up all the work that's being done from 1 to 3. So if we plug in 1, multiply it by a width, that's the work at that point. And then we plug in the next number, that's the work at that point, and then so on and so on. And we're adding up all of these works as we go through there. So you can kind of think of it like little forces being applied through the entire thing, adding it up to give us our total work. So by taking the integral, again, we go off to infinity, and it fills it in. So you can see all these tiny, if I can get it a little bit smaller there, you can kind of see it. All of these tiny little works that are being applied, and we're just adding them up because it's variable, not constant. So there is a variable force that has to be applied through all of them. You can see how thin our rectangle is right there. And so the integral just tells us as we go to infinity the total work that needs to be done. So it really is that simple. It's our force times the distance that needs to be applied, and then we're adding it up from 0, 1 to 3. So let's try another one. So this one's the same thing. We're going from 7 feet to 10 feet with a variable force of 5/4 x dx. So if we plug that in our calculator, I know they're done easily, but we just want to make sure we're doing these correctly. We get 31.875. Foot-pounds. And so again, this is just the height times the width, and it's a very, very, very thin rectangle, and we're adding them up from 0 to 10. So that is our work, and it's adding up all the work from 0 to 10. So it looks like this. Again, that is a thickness of dx, and the height is our function. You can see it there. But then when we take the integral, it fills the whole thing in, calculating all our work. So you can kind of see that's super thin. That would be the work right there for 1. Obviously, it's only at 200, so it's not quite right. That's insanely thin. But that would be that work for that tiny little sliver. So the way I like to look at it is the force is the thing that, like, you have someone who's just hitting it. And to move it, that little thing, he has to hit with this force at x. So if you plug in 7, that's the force he has to apply to just kind of like get it to tiny slide. And you just keep hitting all of those forces. And so adding it up, that's how much work this guy has to do to move it. So 31.875 foot-pounds.